Welcome to the webinar on quantum computing applications in the financial sector, which is jointly organized by the Keene Institute and the NC State University IBM Q Hub. I am your host, Eric Geisels. I'm a professor of finance at the Keene and Flagler Business School and a professor of economics at UNC Chapel Hill. I actually said good morning, but it is midnight in Japan, and I'm grateful for Tomoki Tanaka to stay up late so that he can talk to us today. Tomoki Tanaka is a vice president at Mitsubishi Financial Group, and he's also affiliated with Keio University. He's going to present actually joint research with colleagues from the Quantum Computing Center at Keio University in Japan, which is like the NC State Q Hub, also an IBM Q Hub. We are joined this morning by one of his co-authors, Dr. Suzuki. Welcome. Tomoki is going to talk about amplitude estimation via maximum likelihood of noisy quantum computer. That's a very important topic. We talk a lot about the computational advantage of quantum computers, notably the quadratic speed up in things like Monte Carlo simulations. So this paper actually pertains to methods related to Monte Carlo simulations and the quadratic speed up, but it deals with the possibility or the actual reality of quantum computers being noisy. A few housekeeping rules before we start. At the bottom of your screen, you have a Q&A tab. Please feel free to write your questions, and selection of the questions will be asked to Tomoki at the end of his presentation. I'd like to pass on the word to Tomoki now. Thank you for accepting our invitation. And as I said earlier, thank you for staying up so late. You're on. Go ahead. You can share your screen.
Okay. Just a moment. Can you see the screen? Okay.
It's perfect. Thank you.
Okay. Oh, thank you. Thank you for the introduction. So good morning, good afternoon, good evening. So I mistake the time difference. So now in Japan, 24 in the evening. So I'm Tomoki Tanaka. I'm from Mitsubishi UFJ Financial Group and called MUFG in Japan. And I'm from Keio University, which is the IBM Q Hub, and I'm in Keio University PhD student. I would like to thank you for giving me opportunity to talk today. I introduce one of the achievement of Keio Q Hub financial team. I mainly present the contents of 3 papers related to maximum likelihood amplitude estimation. So this is a disclaimer, so I skip. So this today's agenda is here. And first, I introduce our company profile and I introduce IBM Q Hub financial team. And next, I explain the background. Then section 234 is the main topic of maximum likelihood amplitude estimation. In section 2, I explain the paper amplitude estimation without phase estimation briefly. And this paper proposes that using maximum likelihood estimation, amplitude estimation algorithm is not need to phase estimation. In section 3, I present amplitude estimation without maximum likelihood on noisy quantum computer. As the title suggested, this paper discusses what happens when maximum likelihood amplitude estimation is performed on noisy quantum computer. In section 4, I talk about modified global operator for amplitude estimation. I introduce a new global operator which rotates in a defined space and gain the better estimation accuracy that conventional methods under deploying noise model. So first of all, I briefly introduce my company and the profile of MUFG. MUFG is a financial group equivalent with compliance function and the largest customer based in Japan. We offer financial services including commercial banks, trust banks, and securities, and credit card, and with or so. And I belong to the MUFG and holding company and the commercial bank MUFG bank. And MUFG has a global network and 2,700 offices in over the 50 countries and around 180,000 employees. So next, I explain about initiative for digital transformation of MUFG. In this midterm business plan, digital transformation is one of the essential strategies. And this is figure of the initiative of digital transformation. So for example, blockchain or machine learning or cloud accounting or RegTech or some initiative. So then quantum computing is one of the initiatives of digital transformation. Now I introduce IBM Q Network Hub at Keio University Financial Team, which consists of Keio University and IBM and member companies. Keio University is one of the largest private universities in Japan with over 150 years of history. And Mizuho and Sumitomo Mitsui Trust Bank are also two of the largest financial groups in Japan. And of course, everyone knows about IBM, right? In addition, KOQ Hub has also various other teams such as chemistry team and machine learning team also, with which we collaboration in our research. Next, I explain background why we financial institutes are working on quantum computers. Financial institutes have been expanding their business as IT and technology have developed. Moreover, today we expanded our business by including new technologies such as AI and blockchain. Besides these technologies, we are also focusing on quantum computers, which has the potential of dramatically change the existing businesses. One of the main target application is Monte Carlo simulation. Financial institutes run simulations and calculate the derivative pricing or financial risk or so. The more scenarios are simulated, the better the calculation accuracy can be. But it costs a lot of money and time. In particular, the longest calculation requires more than 10 hours each day, and we want to make them more efficient. And many papers have already been published. For example, Xanadu, IBM, JP Morgan Chase, Goldman Sachs, and so others. And this is attracted the attention of financial institutions around the world. Therefore, we started our research by focusing on amplitude estimation algorithm that can be used Monte Carlo simulations and some other applications, and has quadratic speed. Other point of the about this, so to develop the quantum algorithm, we need to aware that we are now living in the NISQ area. As you know, NISQ is a noisy intermediate scale quantum, so only a few 10 or few hundred noisy qubits. For the quantum computer in NISQ area, there are several considerations, such as first, the limited number of qubits. Second is the limited of computational time, that is the limited number of gates. The third is the effect of noise. With these points, we have suggested a new method, maximum likelihood amplitude estimation, which can reduce the number of qubits and gates to perform quantum amplitude estimation. So first, I explain maximum likelihood amplitude estimation briefly. So if you want to know detail, please check this QR code. Or in the conventional amplitude estimation method, two integrates are required. So the amplitude amplification and inverse QFT. As you can see, there are many control gates and perform inverse QFT. So in the conventional method, we propose a new method which does not require inverse QFT. This performs amplitude amplification in parallel and combine these results by using maximal likelihood estimation. This method can remove the inverse QFT and a lot of control gates with keeping the quantum advantage. So in one example case, this method has two advantages. One is to keep constant of the number of qubits equal as the required accuracy. Other is to reduce the number of gates. And we have opened up this code on Qiskit. Qiskit. Again, we now living in NISQ area. So this method can reduce qubits and gates. So next, we research about the effect of noise. Now we have tested what happened on the real quantum device IBM-Q, including noise. So this figure shows the result when the real quantum device IBM-Q balancer is used. The horizontal axis is the number of MK, and that is the number of amplitude amplification. And vertical axis is that the hitting ratio of answer qubits being 1. The green dot is the real result when the real device is employed. As you can see, with an increase in the number of MK, the rate of approach to 0.5. That is the mixed state. In other words, the longer the depth, the more information is lost due to the noise effect. To explain the decay rate, depolarizing is taken into account and a corresponding formula is obtained to fit the experimental result. The fitted result is shown the blue line in this figure. Based on the result of real quantum devices, we introduce depolarizing channel and calculate some value of probability, Fisher information matrix, and Cramer-Rao band. Today, I will skip detail, but if you're interested, please check our paper on arXiv. One of the important points is that we need to perform a multi-parameter estimation. This is due to the fact that extra parameter characterizing depolarization, which we call the noise level kappa here, is also unknown parameter. The noise level will correspond with target value A. In addition, we are aware that IBM-Q are calibrated almost every day, so that the state of device are changing. So this is the, one of the most important points I want to converse in this talk. We analyze the Cramer-Rao band. It is well known that the Cramer-Rao band given a lower bound of estimation error. This figure shows the relationship between the number of query and estimation error. As shown in this figure, as the number of query increasing, so the estimation error is reduced. The red line is here, is the classical random sampling, and orange line here is the result of maximum likelihood amplitude estimation in the absence of noise, which shows the quadratic speed up in comparison with the result of classical random sampling, red line. So, and color dots are the lower bound of estimation error in the presence of noise. And the color green, blue, and light blue corresponds to the different magnitude of the noise level. In this slide, we enhance the following 3 points. First is the limit of the achievable estimation error. In the depolarizing noise in its presence, it is impossible to get the better estimation error even though the number of queries increases. For example, here, so number of increases the number of queries, but estimation error is not reduced. Second is the effect of noise, effect of the noise level value. For example, compare the green and light blue. Light blue provide a better estimate. So this indicates that better estimation can be obtained when the noise level is lower. Last is the possibility of NISQ device. For example, light blue line when the kappa is 0.001 up to the point of showing the star. Almost the same estimation error can be obtained in comparison with the noiseless Cramer-Rao lower bound shown orange line. This indicates that the quadratic speed up is possible in the presence of depolarizing noise, although the number of queries is limited. So this slide shows the result of integral integration of sign function by using real quantum device IBM-Q Valencia. The green line is the Cramer-Rao band when amplitude amplification is performed, and blue dot line is the result when the real device is used. In this slide, we note the following 2 points. First, the fact that the green line and blue dots are well overlapped indicated that experiment result also attains the theoretical lower bound of estimation error. And second, the estimation error experiment obtains the shown in blue dots always exceeds that of the noises case shown in orange line. But on the other hand, some estimation errors experiments obtained shown in blue dot are less than the theoretical limit of the estimation in error in classical random sampling in the red line. Then we evaluate the hardware requirements to perform the five-dimensional integration based on our analysis for noisy effect of quantum device. This table shows the required and current performance of quantum device to execute the integration. We find that there performs a gap between real and required quantum device. For this analysis, we believe that it is important to find what we can do as the hardware of error boost. In addition to improvement of performance of real hardware, it is also important to improve algorithms, for example, to support the effects of noise. So we propose improvement of the algorithm. So next, I explain the third paper, modified global operator for amplitude estimation. Assuming the depolarizing noise model based on the real quantum computer, there are the gap between the classical Fisher information and quantum Fisher information. So such that there are the gap between the classical Cramer bound, so green line, and quantum Cramer bound, orange dashed line. That is, there is the still room improvement in this gap. So then we introduce the new operator, modified global operator Q. The conventional operator G rotates a space spanned by psi 0 n 0 and psi 1 n 1 with angle 2 theta. So here. So now we consider a new operator Q in another space with a dagger action to the left space. So here. So this operator Q rotated right space and so spanned by 0 or 0 and phi with angle phi and with angle 2 theta. Rotated angle 2 theta. So this is, we can predict that amplitude estimation task can be performed even this operator Q. So with the operator ready, we calculate Fisher information to examine the theoretical lower bound of estimation error. The lower bound is the smaller is better, and the lower bound is in an inverse relationship with Fisher information. So that Fisher information is the bigger is better. First, in the absence of noise, the four values, classical Fisher information and quantum Fisher information in G and Q, the same. So since the Fisher information of G and Q are the same, we can see that Q, the new operator Q, can put out about the same performance as G in the absence of noise. So, and since the classical Fisher information and quantum Fisher information are the same, there's no room for improvement. Second, in the presence of depolarizing channel, the four values are not the same. Quantum Fisher information of the G and Q is the same. On the other hand, classical Fisher information of Q is bigger than the classical Fisher information of G. That is, our method Q can produce better estimation error in the presence of depolarizing channel. So we execute numerical simulation assuming the depolarizing channel. The green line is the dots the conventional method of operator G, and the red line is the proposal method of Q. The orange line is the quantum Clavell lower bound. Using our method, we can gain the better estimation accuracy than conventional method. So this is the last page of my presentation. I introduced our 3 papers about quantum amplitude estimation algorithm. And so it is important to collaborate through open innovation to contribute to the development of science and to make quantum computer usable. So it is very important, I think. So thank you. Here is the presentation.
Thank you, Tomoki. I was a bit worried at the beginning of your presentation because the paper is very technical, and the presentation, the beginning was, I was worried it was not going to be technical because I've prepared some comments that are more technical in nature. So let me share my screen. I enjoyed your paper. There's a lot. I mean, there's more than one paper actually, as you stated at the end. Let me share my screen and give you some thoughts and comments. There's a Q&A also, but let me get. This is I'm going to start with an equation that you actually put on your slides. I can't remember which slide it is, but it was appearing on one of the slides. This is the probability of observing one of the states when it is contaminated by depolarization noise. And what you notice from this equation is that, I mean, this is the way you write it, but you can rewrite it this way, is that since P is between 0 and 1, which is the probability of 1 minus the probability of a noise, what happens is that as you increase M, this goes to 0, this term. And when it goes to 0, you've got a problem with identification of theta, which is the parameter, which is your parameter of interest. Theta here is defined as via the sign transformation. Now that brings up a question that I have, that I'm struggling with. In the asymptotics, you basically are dealing with this kind of normalization of samples, of quote unquote sample size. And it is a combination of this M, which governs the pattern of these M's here, the sequence of M's here, and the number of samples that you draw from, which is this NK. This can change across the M's. Okay, and you have this product of these. You have the sum of these. You sum up to N. So the asymptotics seems to suggest that you can trade off M and N, and they play the same role. But I don't think that is the case actually. And one of the things that, coming back to this above equation, if M grows, then you have to deal with quote unquote weak identification. something that we call weak identification. That is to say, as the powers here, you're gonna start losing information about theta. And as you start losing information about theta, you no longer have the central limit theorems that the standard central limit theorems. In fact, you do have no longer convergence in distributions results, and there is and no longer a Cramer-Arrow lower bound actually. And so there's quite a bit of literature on weak identification particularly in econometrics, a field that I'm more familiar with. And so it's just a clarification, because I think you sort of tend to not be very careful about M versus N trade-off. And the framework seems to be suggesting that one might do both, either one of them. So that's the first thing. But this thought led me to think about something which might be much simpler than what you're doing, a suggestion. And this comes back to likelihood theory. There's something known in the likelihood theory that is known as profile likelihood estimation. It goes back to Euler, Barndorf-Nielsen, and Murphy and van der Vaart have a very nice. I will send you my slides, and there are references at the end of my slides. What it does is the following: you can fix kappa. That's the noise term. I mean, it's which go to the previous slide. It is minus the log transformation of p. So you can fix kappa, and we sort of have quite a good idea about what probability of noise there is in these systems. So you can fix kappa, and you can fix kappa on a grid that we have a lot of, I mean, I hate to use the word priors, but you have a lot of information about. And the idea of profile likelihood functions is the following: is you don't want to estimate the entire parameter space, because for a number of reasons, one of the reasons being that the likelihood function might be too complicated. And when you only estimate a subparameter, it's much easier. And that was the original motivation for profiling of the likelihood function. In this particular case, you only care about estimation of theta A. And you could fix kappa. You have on the quantum machine, you have the gates for fixed kappa. And you have the quadratic speed up that is in your previous work that you alluded to. So why not compute on a fixed grid, given kappa, your previous way of doing amplitude estimation, and then you just compare the output, and you pick from the various kappas that you picked, and you pick the one that yields the maximum likelihood. So you're not really engaging in estimation of kappa jointly with theta. You're solving that problem much easier. And there is a fairly established theory on profile likelihood estimation that you might rely on. Going to be much easier to deal with. There is another issue that is you might want to think about. The model that you use for errors is a very specific model, and it may not be the right model. Now, in likelihood theory, in maximum likelihood estimation, we have a way of dealing with that. So the Cramer-Arrow lower bound, the way you compute it based on the outer product of scores, is no longer valid because in that particular case, the outer product of scores is no longer equal to the Hessian, which is the Fisher information actually. There are sort of robustifications of your computation of your variances based on what's sometimes called quasi-maximum likelihood. The other thing is that a number of objects in the paper, and I just give you one here, they're kind of ill-posed because A hat converges in probability to A, and therefore is asymptotically degenerate. So this is an ill-defined object. It would be more correctly to think about some normalization of NQ, and this comes back to what is NQ, what is driving it, and what's driving the asymptotics actually, and where the delta is the usually square roots or the delta equal to 1. And this comes back also to some of the plots that you were showing during your presentation about the quantum Kramer-Rao-Lehr bound as opposed to the classical Kramer-Rao bound. It wasn't clear whether that was due to the convergence rates or whether that was due to the actual information. And I think it's due to the convergence rates, but it would be nice to actually separate that out actually. So anyway, I thought I really read with interest your paper, so don't get me wrong. I'm just trying to think about ways to actually make it better. So that was the purpose of my talks. I will send you the slides. These are the references, so you can get them. So that, for what it's worth, do you want to reply or say something about this, or do you get to the Q&A first?
Hello.
Oh, yeah. Hi. How are you?
Hi. Fine. Thank you. So many questions, but I agree that that this presentation a bit technical. So about the first question. So actually, yeah, your comment is right. And could you please show me your slide? Yeah, actually, yes, thank you. Oh, yeah, I am a co-author of this paper.
Yes, I know. Well, welcome. And I see you. I see you went to the office at midnight
Okay. So actually, as you mentioned, that exponential minus kappa m represent a kind of noise effect. So as you pointed out, the number of m increase, the P of P2 m to 0. It's right. So this means that capital P approaches to 1/2. That means completely random.
Yes,
so in that sense, as you mentioned, that theta A, we cannot identify theta A because of the loss of the information.
That's right. That's right.
Yeah. And the second question is...
So by the way, this is an asymptotic argument, but you have to be careful that as you increase m, you're gonna face this problem gradually. So that's the
right
convergence problem.
Yes.
Anyway,
maybe yeah, actually Tanaka-san showed that a kind of decay of the decay of the estimated error, that in the large M region, the error will not decrease. That means that all of information is lost because of the noise. Okay.
You want me to go to the next slide?
Okay, so many questions. Okay. Okay. I'm really interested in this comments. Maybe actually that namely the kappa is a kind of
it's a nuisance parameter.
Yes, right. So in that sense, we try to get rid out kind of the problem. That you're right. So it is a one candidate to eliminate the parameters kind of by using a profile likelihood estimation.
And I think it's much simpler because you're gonna basically avoid all the hard work of trying to estimate your kappa. You can just put this in. You can put this in parallel. Just compute it for a few on a grid and get solve the problem.
Yeah, actually, yeah, you're right. I completely agree. And we are struggling to find a kind of eliminate the nuisance parameters. So you're right. Actually, I'm really interested in the kind of your suggested paper or materials. If it's okay with you, could you please send?
Yeah, I will send it. Maybe I don't want to monopolize this. And I mean, we can go over it, but let's maybe go to also some of the questions from the audience. If I may stop sharing my screen. Okay, so what is the max circuit depth before MLE fails on an IBM hardware, say Valencia?
Actually, Tanaka-san is basically made the programming. Actually, I think the depth is also depth is important. However, I think that the number of the CNOT gates or some single gates, how many gates to何ゲートぐらい使える？ How many?
So I share the slide. Just a moment.
Oh, you have slide, yeah.
So yeah, so one MK is have 5 CNOT gate.
CNOT gate, 5 CNOT gate.
5
yes.
CNOT gate. So here is 200 CNOT gate here. But
yeah, yes, please.
So here is 1, 0, 1, 2, 3. So here is MK is 4, and so CNOT gate is 20, about 20.
Yeah, point is basically we use a kind of 2 types of gates to simulate the Monte Carlo simulation. One is a single gate, single qubit gate, and the other is a two qubit gates. Actually, the number of the single gates and the 2 qubit gates is a total amount of the gates, but currently the main problem is a kind of error rate of 2 qubit gates. We believe that the number of CNOT gates, namely, is important to consider.
Yeah.
So in that sense, we can say how many depths of blah blah blah, but the problem is the number of CNOT gates, 2 qubit gates. Currently, we can use 5, 6, 7, or something around that.
So here is CNOT gate is 5.
Yeah. Okay. Around 5.
Around 5. Around 10. Around 12, 20, 40.
Yeah.
80.
Currently, a kind of around 10 CNOT gates is a kind of maximum.
Okay. So the CNOT gate is a stumbling block on this, as you point out in. This, by the way, relates also a little bit to the profiling, because if you profile in parallel on different gates, you're gonna have to assume that the kappa is the same for all the gates that you profile on. So this is an aside, but it's something that you're gonna have to deal with as well.
Yeah.
I don't see any other questions unless someone else wants to join this conversation.
Yes, actually, so as you pointed out, that this presentation is a bit technical. So I'm just at the comment that the kind of, comments that what we accomplished is that maybe, but usually it is known that the quantum algorithm, that makes the Monte Carlo simulation faster. But the usual known algorithm is a very, how to say, known algorithm need to perform a kind of very complicated, should use a complicated algorithm, namely the quantum Fourier transformation.
I know.
This is a bottleneck. So in that sense, and without using the inverse Fourier transform, we found that the kind of algorithm low cost, but it's possible to make the quantum speed up. But that is the initial our suggestion. The point is here, in that moment, we do not consider any noise, we do not consider any reality, a kind of real device. The Tanaka-san introduced a kind of how to incorporate a kind of noise effect. And he showed that the kind of, including the noise effect, we show the kind of how to deal with the noise effect, and we try to.
No, so, I mean, this is pretty clear from your paper, and which I think is really the key insight, is that by adding on this model of noise for the depolarization, you get the speed ups that you sort of have on the noisy machines. So I think this is the genuine contribution of the paper, and so the comments I was making is just to make it better in terms of what you're trying to do. I think I've seen some of your papers, notably the very early paper I think was presented at the IBM Q-Hub meeting, and I really saw a presentation of it, and I got really interested in it. So this is good stuff. So I'm really grateful that you will participate it. In the interest of time, since it is late for you guys, I would suggest that we end it here, unless there is anybody who wants to file a question in the Q&A. Which thanks to all of you for participating. I'd like to finish by saying that we have our next webinar on January the 14th. We will have Daniel Egger, whose work was actually mentioned on one of the slides, from IBM Zurich. And he will talk about warm starting quantum optimization. Thank you all of you for participating. We will see you after the new year. Stay safe, and thanks again. Thank you. And I will send you my comments to both of you, Tomoki and Dr. Suzuki. Thank you very much.
Yeah, thank you very much.
Thank you, bro.